Hello and welcome. I'm Haihao John, and in this video, I am incredibly excited to walk you through our latest work, Enhanced Event-Based Dense Stereo via Cross-Sensor Knowledge Distillation, which will be presented at ICCV 2025. First, let me introduce some background information. Stereo matching mimics the human binocular vision system. It estimates the distance to an object by comparing the differences between two viewpoints. It is widely used in scenarios such as 3D reconstruction and autonomous driving. The method for stereo matching based on RGB images is relatively mature. However, due to the problems of motion blur, dark light blindness and overexposure of strong light on the sensor, it is not suitable for stereo matching to estimate depth values in harsh scenes. Event cameras independently capture short-term brightness changes with microsecond temporal resolution, offering the advantages of low latency and high dynamic range. They provide reliable information for visual tasks in high-speed motion and extreme lighting conditions, and offer a new approach to stereo matching in harsh environments. We categorize existing methods based on the input modality. These methods can be divided into two groups: pure event methods and combined event and RGB methods. These methods maintain the same number of input modalities during training and testing. Pure event methods lag behind in performance, as the spatial sparsity of events significantly increases the difficulty of obtaining dense disparity. This has led to a trend toward combining RGB with stereo matching. While these methods have achieved the best performance to date, they use both modalities as input during testing. This means that even after events are collected, the model must wait for RGB to be available before a result can be input. This sacrifices the low latency characteristic of events. Furthermore, the simultaneous input of both modalities increases the computational burden, hindering practical deployment. Therefore, we sought a method that maintains low latency while also extracting information from RGB to achieve improved performance. There is an old Chinese saying, "It is better to teach a man how to fish than to give him a fish." The combined event and RGB approach is essentially giving a man a fish, but simply giving the RGB information to the event, making the event heavily dependent on RGB. We seek to explore a method that teaches people how to fish. Rather than simply giving the RGB information to the event, we instead allow RGB to teach the event how to acquire structural information during training. During inference, dense disparity estimation can be achieved with only the event input. Specifically, we attempt to perform cross-sensor distillation from RGB to event. During training, we input both modalities to fully extract information from RGB, while retaining only the event during inference. This allows us to extract rich structural information from RGB while preserving the low latency characteristics of the event. This process presents two challenges in implementation. Due to the significant modality gap between events and RGB, directly aligning their features would contaminate the original. Furthermore, the model has two inputs and two feature alignment losses, which can lead to loss imbalance. Therefore, a thoughtful strategy is necessary. We distill as much RGB information as possible into the event without contaminating the original modality. Our method consists of two branches, an event branch and an RGB branch. During training, we fully extract information from the RGB branch and distill it into the event branch. During test, we retain only the event branch, achieving dense stereo matching while preserving the low latency characteristics of the event branch. Specifically, we implement a multi-level distillation strategy. Shallow features contain a lot of modality-specific information, and extracting them into the event branch can obtain complementary cross-sensor information. However, shallow features suffer from significant modality gaps. Simple alignment can contaminate the original modality-specific information and introduce noise. To avoid this problem, we adopt a comprehensive strategy from the perspectives of long-range and focal points. For deep features, we adopt a direct alignment strategy, as they primarily contain task-relevant contextual information. In addition to the distillation strategy, to ensure cross-view consistency, we design an intensity event joint left-right consistency module. This module seeks to enforce pixel-level consistency between the left intensity image and the warped image, which implicitly indicates the quality of the estimated disparity. We conduct extensive experimental verification on a large number of real-world datasets, and the quantitative results of MVSEC demonstrate the advancedness of the proposed method. The proposed method fully extracts extensive dense and structural information contained in intensity images and distills it into the event branch during the training, making its performance significantly better than existing event-based stereo matching methods. We perform extensive experiments on the MVSEC dataset to fully validate the effectiveness of each proposed component and related design choices. We first present the results of the ablation study. It can be observed that all the proposed components have contributed to the superior performance. This indicates that the information derived from intensity images is effective for dense event-based disparity estimation without significantly altering the network structure. For further exploration and discussion, we present our experiments to validate the design choice of the feature distillation module, as it brings the most improvement among all the proposed components. Specifically, to solely examine the effectiveness of our proposed shallow distillation, we compare it to the simple alignment feature-level distillation methods. MSE is a baseline method that simply minimizes the element-wise L2 distance between the features of the teacher and student. As shown below, directly aligning the features of the two modalities contaminates the original modality-specific information and introduces noise to the event branch. That is all. Thanks for your attention.